Okay, IBAISL2. We are done with chapter 6, which has been all about correlation and lines of best fit. Linear regression really is what it should be called. We first started talking about correlation. I realized we did correlation by eye in the previous target, but now we had a much better way to talk about correlation. You should know the different types of correlation just by looking at a scatter plot. Oh yeah, we should maybe throw that in there. Maybe put a little scatter plots right here. Scatter plots. From scatter plots, you can see if the correlation has a linear trend or a non-linear trend. I'll never ask you if it's like a quadratic trend or an exponential or something like that, but right now you should know the difference between a linear trend and a non-linear trend. Non-linear being there's some sort of curve to it. You should be able to talk about the strength of the correlation. The way we talk about the strength is we find Pearson's correlation coefficient, which is lowercase r. The way that I've showed you guys how to do this on a TI graphing calculator is to use linreg. Remember, if you run linreg and you do not see your r value, you need to go to catalog and turn the diagnostics on, or diagnosticon as I call it. Be ready to use descriptors for correlation, such as very weak, weak, moderate, and strong. Remember that there's cutoffs for those with the R values. I think it's like 0.25, 0.5, 0.75, and 1.0. Also, I guess another descriptor we could add in there is that sometimes, if it's a negative R value, you could say it's negative. The negative positive is kind of interesting with correlation because it tells you whether or not, as one increases, if the other one increases or decreases. We've also been doing lines of best fit. All of these are in a y equals mx plus b form. The first way we did it is we did a scatter plot and did a by eye method. The by eye method was finding the mean point, which was x bar comma y bar. It's the mean of x and y, and then you plot it as a coordinate. Then the by eye method, you make it go through a line of best fit, go through that point, and try to get about half the data points above and half below. A better way to find a line of best fit is the least squares regression. Least squares is that big gnarly formula with all the other little formulas that fit into it. I think we did one example by hand. Remember that the least squares are trying to minimize residuals. Residuals are like the distance from the points, the actual data points to the line of best fit. Then we quickly switched over to finding a linear regression line with the calculator, which is a y equals mx plus b using linreg. Then your book threw in a little section on piecewise functions. So I suppose, we could have a tiny problem on piecewise functions. The last thing, I'm calling it data applications, but that's just a fancy term for word problems. That there might be some sort of contextual word problem with a data table, and then I need you guys to maybe find the correlation, find the line of best fit, and I will ask you to interpret the slope and the y-intercept. Remember, if your slope is rise over run or change in y over change in x, that might mean something in terms of the problem, cups, GPA point changes per cups of coffee or something like that. I did on the warm-up the other day talk about interpolation and extrapolation. Remember, interpolation is that when it's within the data, and then extrapolation is when it's outside the data. Sometimes they'll ask you, is extrapolation appropriate in this case? That's really just them talking about the correlation strength. If you have a weak correlation strength, extrapolation is not really appropriate. But the higher the correlation strength, the more confident you could be in extrapolating. I feel like interpolating is always kind of cool, unless you have just a terrible R value. But extrapolation is where it gets tricky and you need strong R values. Okay.